Okay, everybody sitting with somebody? Good, everybody has a worksheet. Great. Be sure to sign in when the sign-in sheet comes around. Happy Monday, everybody. Remember, we do have recitation tomorrow. It's going to be a really interesting recitation. Well, I may or may not bring cookies, but these days it's tricky because my cookies that I make have butter and wheat and nuts and chocolate, so I'm not really allowed. So it's a dilemma. I might bring cut carrots. There might be cut carrots at recitation. All right, so here's a review of Friday. Friday we were discussing section 5.3, the valuation theorem. Remember, it was a relationship between definite integrals which, you know, is assigned area. SA, so that's a number. And the evaluation theorem says that this is actually equal to this calculation involving an indefinite integral. And remember what the indefinite integral is. It means the general antiderivative. So over here is a calculation involving antiderivatives. Find the general antiderivative and do this with it. Or find any particular antiderivative and do this with it. So F is any, capital F is any particular antiderivative of little f. So that's the end of meeting part one, reviewing what we did on Friday. Thank you. All right, meeting part two, section 5.4. Is about area functions. So this symbol so I'm going to do t equals a to t equals b. And I'm going to change use the letter t as the variable. So this is the number that's the signed area under the graph of f from a to b. So a and b are actual numbers. This is a number. So now we're going to replace the number b with a variable x. So notice, again, in this expression, this is a number. If you want to say that t is a variable, well, you know, from the outside you don't see the variable. This is like a black box, and all it produces is a number. You don't know how it got it. Just something went on inside that black box. But if I replace b with the variable x, I get this. This is no longer a number because I don't know the value of x. So this is waiting for us to choose a value of x, to pick an actual number for x, and then we can get a number that's the signed area. So this is a function. And I'm going to call this g of x. This is what's called an area function. For f. So g of x is an area function for f. Now inside this black box, there's f of t, but we're thinking about starting with a function f of x, get rid of the x, put a t in there, build this thing. And so the way it works is you choose the value of x, and then what I have to do is compute, is to find the signed area under the graph of f from a to x. And then whatever that number is, that's that area, that's the output. All right, so in your groups of 2, you should have a worksheet. I want to discuss this together at the start of it, and then I'm going to let you all work on this. So we've got a function f of t here. And we've got a function g of x that's defined this way. So g of x is an area function for f. So we have a graph of f, but we don't have a graph of g. So the goal is to build a graph of g. So we want to make a table of values for g. So we want to fill in this table. And we want to use this table of values to make a graph of g down here. So let's think about this. Let's think about what's going to go in the entry of this table with x equals 4. Well, when x equals 4, we're talking about the area under this graph from 0 to 4. And we're going to have to do that, going to have to think about that 8 times. So let's turn this paper over and let's label these x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, x equals 5, x equals 6, and x equals 7. So for x equals 4, for this one, we need to figure out the signed area from t equals 0 to t equals 4 under the graph of f of t. So that's what we're going to be figuring out, is the value of that area. And that area is going to be what we put in that table. So let's figure it out. On this graph, here's t equals 0, here's t equals 4. We have to figure out the signed area. Well, I'm going to break this up into a number of regions. First of all, there's this square. There's this triangle. There's this triangle. These are all above the axis, so I'm coloring all these in green. And then there's this red area, the lake of fire, that's down here. And so that is... I made a mess of my paper. The signed area is going to be, well, let's see, this square is going to be 2 by 2 plus that next triangle, which is 1 by 2, so 1/2 of 1, that's the width, and the height is 2. And then the next green triangle is going to have area 1/2 of 1 times 4. Those are all positive because they're above the axis. And then I'm going to have a minus sign here, and then the area of that red triangle, which is 1/2 of 1 times 1. So when you add all those up, let's see, this is going to be 4 plus 1 plus 2, that's going to be 7, minus 1/2. So this is going to be 6.5, or 13/2. So that's the value of that signed area. So on the previous side of the page, that's what goes here, 13/2. And on this graph, when t is equal to 4, 1, 2, 3, or when x is equal to 4, the y value is there, 6.5. So we've made one data point. All right, so now I'm going to shut up and I'm going to let you in your groups make all those other graphs. You've got 7 more graphs to color in, and yep. I guess you could pause that if you and discuss this. Anybody want to call out the numbers that go in these cells? Like for instance, when x is 0, what's the value of g? 0. How about when x is 1? When x is 2? 5. When x is 3? 7. We already did 13/2 when x is 4. How about when x is equal to 5? Back down to 5. How about when x is equal to 6? Back to 3. And when x is equal to 7? 2. So the regions that I get look like this. A different area function for each value of x. I'm sorry, a different signed area for each value of x. Okay. So that was meeting part 2, the idea of an area function. Meeting part 3 is about differentiating area functions. All right, so this thing is g of x. So what is the derivative g prime of x? So in other words, get the expression that represents g of x. The integral from t equals a to t equals x of f of t, and park this in front of it, d dx. What is that? Now, this is a blast from the past. A couple months ago, we were talking about what the derivative was. This means we do the following. The limit as h approaches 0 of g of x plus h minus g of x all over h. Remember that? Change. Remember this is a change in y over change in x. This is a difference quotient, it was called. In this expression here represents the slope of a secant line on the graph of g. And then when you park the limit expression in front of it, that pulls that second point closer and closer and closer, and this represents the number that's the slope of a tangent line. So let's think about the numerator. Of this expression. I'm going to color that just because just because I have all these colored chalk that I can lord over you. So the numerator is going to be g of x plus h minus g of x. Now let's make a picture of what that looks like. So this is a picture with t as the horizontal axis and f of t as the vertical axis. So here's my graph of f of t. And I'm going to be interested in the signed area from x equals a to x equals, t equals a, and t equals x, and then also t equals x plus h. So let's start with the signed area from a to x. So that's this region. So red is g of x. It's the signed area under the graph of f of t from t equals a to t equals x. Now let's think about this area, starting from a and going all the way over to x plus h. That's colored white. Overlaps a lot. So white is g of x plus h. And so this yellow region in here is that. So yellow is, that yellow region is g of x plus h minus g of x. And we're interested in the number that's that area. Now, it looks like that's a trapezoid, and if it were, it'd be great, because then we would have a formula for the area of a trapezoid, which I'm sure that you all know as well as I do. And we could just use that formula to get the area. But the thing is, this is not a trapezoid. This is a curvy graph. So this is a funky shape with 3 straight sides and then a curvy top. But that's okay. We are familiar with the idea of approximating regions with rectangles. So let's approximate this this yellow region with a green rectangle. So let's look at that green rectangle. First of all, it's a left rectangle. So the left, it touches the graph of f at the rectangle's left edge. So this point has coordinates x and f of x. And this rectangle has width h. It's a bad choice of letters, right? You really want the height to be h, but it's the width in this picture. So the green area, so the green rectangle area is height times width. And that's f of x times h. So here I should have said this is the yellow area, and that's approximately equal to the green area. Which is f of x times h. So the numerator is this expression, and it's roughly equal to this. And the closer, the skinnier those rectangles get, the better this approximation gets. So we get that g of x plus h minus g of x, all of that divided by h is going to be approximately equal to f of x times h, that green thing, divided by h. Now that ratio, it looks like you could cancel h, but we have to make sure we know that h is not 0. Well, remember, we are considering the limit as h approaches 0. So that tells us h is not 0. So that tells us g prime of x is the limit as h approaches 0 of g of x plus h minus g of x all over h. But that means I'm doing the limit as h approaches 0 of this thing, f of x times h over h. So again, since h is approaching 0, we know that h is not equal to 0, so we can cancel. So this is just equal to the limit as h approaches 0 of f of x, but that's just f of x. So we get that g prime of x is f of x. That is a weird thing. You build this bizarre thing called an area function, and you take its derivative and you get f of x. So what you've built when you build the area function is you've built an antiderivative. Well, so that's such an important fact that it's given a name. It's called the fundamental theorem of calculus. So things are getting really weird. Things have been really difficult. So this should strike fear into your heart. This is the fundamental theorem of calculus, part 1. Dun, dun, dun. So it says that if you build one of these area functions, and I'm not going to bother calling it g. I'm just going to say that there's my thing, and this is a function of x. And if I take the derivative, what the fundamental theorem of calculus says, ftc1, it says that this is f of x. It's pretty amazing. So if you go back and look at your handout, we're now ready to do part the bottom part of that worksheet. So, first of all, if we plot these points, So we had a y value of 0, of 2, of 5, of 7, of 6.5, 5, 3, and 2. So there was our graph of g of x. It's a pretty cheesy graph because, you know, we don't have many data points. Now, let's answer these questions. This question says, what's the value of g prime parentheses 2? Now, it says answer without using the graph. Well, I can't resist using the graph because the graph's just right there. So g prime of 2, remember that means the number that's the slope of the tangent line. Well, if you go up to the graph, when x is 2, well, I don't know what this slope is. It's kind of, again, it's a cheesy graph, and I just made a really, like a first grader's tangent line. It's really hard to figure out the slope. Maybe 3, maybe 2, maybe 4. But let's go back down and look at the question again. What's the value of g prime of 2? Well, remember that g prime of x is just f of x. That's the fundamental theorem of calculus, part 1. So if I'm asked for g prime of 2, that means I can just do this, get f of 2 by the fundamental theorem of calculus, part 1. So go up to the graph of f, go to the place where x is equal to 2, find the y value on that graph. Well, this is the point 2, 4. That y value is f of 2. So that's the number 4. So you see that this picture of mine, again, I gave all these disclaimers about how I'm, you know, sleep deprived, had too much coffee, and whatnot. I'm just generally fuzzy-headed, so I'm not really confident in that slope of that line, being correct at all. But that number is great. That came right from the graph. The graph of f has a height of 4. So that slope, that tangent line slope is supposed to be the number 4. Okay, g prime of 5, well, that's going to be the same as f of 5. So we go up to the graph of f of x, over to the place where x is equal to 5, and on this graph, this point has coordinates 5, -2, and so that number, -2, is f of 5. Now, if you go back up to the graph of g, when x is equal to 5, 1, 2, 3, 4, 5, here's the place on the graph where x is equal to 5. The slope of this line, if this graph were drawn better, would be the number -2. Now, where does g have a local max? Okay, well, on this graph, it looks like at x equals 3, because that's where g stops going up and starts coming down. But again, I don't have a whole lot of confidence in this graph. I don't have data points in between these particular data points. But I'm going to say around x equals 3 because g changes from increasing to decreasing. Oh, but if g is changing from increasing to decreasing, what does it tell you about g prime?
If there's a 0 at g, at f3, or g prime.
No, I'm just talking about g. So if g is changing from increasing to decreasing, that means that g prime, Jonah? You're all working too hard. Let's just this. If g is increasing, what's that tell you about g prime? Positive. If g is decreasing, g prime is negative. So that means that g prime changes from positive to negative. Oh, but G prime is F, so that F changes from positive to negative. F has to change from positive to negative. Well, let's look at the graph of F. That is very clear. That happens exactly at x equals 3. There's no ambiguity there. I wasn't confident in this graph. Again, maybe there was some weird stuff going on and the peak is actually over to the left or right. But no, definitely. F changes from positive to negative at x equals 3. So that's where G has its max. So I'm going to say exactly x equals 3 because F changes positive to negative. All right, this has been really hard, and it's just part 1. Fundamental Theorem of Calculus part 1 is this thing. Everybody geared up for part 2? Fundamental Theorem of Calculus? Dun dun dun, we've already done it. This thing, the evaluation theorem, is actually Fundamental Theorem of Calculus part 2. It's possible to do it as our book does it, where you discuss the evaluation theorem first, and then you discuss this thing. I think historically, this was the thing that was done first. So the fundamental theorem of calculus, and then this is second. So the evaluation theorem is the fundamental theorem of calculus of calculus part 2. So we go over here, the fact that this definite integral equals this calculation with an indefinite integral. This is the evaluation theorem, or it's also now known as fundamental theorem of calculus 2. So you can rest assured that it's not going to get any worse. All right. We have about 17 minutes left, and I think I have maybe about 10 minutes more stuff to do, but I'm not sure. Suppose I do this. There's one of these functions. It's an area function. Now suppose I park in front of it this thing. What is that derivative? Yeah. Say it again?
It's 2t.
No, it's not. The answer was 2t. That would be the derivative of t squared. Yeah. Say it again?
Is it dq over 2?
No. We're looking at exactly one of these things. So this says that to take the derivative of one of these things, you just pluck out the integrand and you replace the t with an x. So f of t is t squared, that's the integrand. F of x is x squared. So this thing, this whole thing stands for x squared. So now let's think about a picture of this. So here's a graph of f of x. It's a parabola. And we've just figured out that an antiderivative of this is this thing, g of x, which is this integral from 0 to x. So t equals 0 to t equals x of t squared dt. If I take that thing and I take its derivative, I get this. But say what you said again. So yeah, so in other words, this thing is an antiderivative of this thing. But we already have a formula for an antiderivative of this thing. We can use the power rule. So I could call this capital F of x is x cubed over 3. Using the power rule, we know how to get an antiderivative of x squared. It's x cubed over 3. So we have two different ways of writing an antiderivative of x squared. One is we can just use the power rule and we can build this function, x cubed over 3. That's an antiderivative. Or we can do this insane thing, which is to build this area function and realize that because of the fundamental theorem of calculus, that's also a way of writing an antiderivative. All right. Now, how about this one? What is this derivative? What is that antiderivative? So I have an area function, the integral from t equals 0 to t equals x of 1 over 1 plus t squared dt, and then I park the derivative symbol in front of it. So what is this derivative going to equal? Yeah?
1 over 1 plus x squared.
Exactly. You just pluck out the integrand, 1 over 1 plus t squared, and you swap out the t's and put x's in there. So that means that we've built an antiderivative of 1 over 1 plus x squared. So if I have this is my f of x, which is 1 over 1 plus x squared. Remember, that looks like this, because when x is 0, this is height 1/2, and then when x gets really big, the y values get very close to 0. And so what we've just found out is if I build this thing, so g of x, if I build this wacky area function from t equals 0 to t equals x of 1 over 1 plus t squared dt, I've built an expression that functions as an antiderivative. The fundamental theorem of calculus says if I take the derivative of this, I do get this. Now, anybody remember though? We've talked about an antiderivative of 1 over 1 plus x squared. What's the function whose derivative is 1 over 1 plus x? Is your hand is sort of up. Yes, wonderful. So we already know that capital F of x is arctan x, which is the same as tan inverse of x. And we even know what that graph looks like. It looks like this. Now, I'm ignoring the fact that there could also be a plus c in any of these. You could move this graph. You could have capital F be arctan x plus 17. That would move it up. Its derivative would still be this. So we have two different ways of writing an antiderivative for this function. This thing that we already knew, or this wacky thing. So, you know, why on earth would you bother with this thing when you've got this perfectly nice, clear function? We know, I mean, as weird as that looks, we realize its graph is going to have to look like this because it's a function whose derivative is this, so it's going to have this shape. So we've seen two examples where we have a way of writing an antiderivative using a formula for a function, and then a way of writing an antiderivative as an integral expression. So here's one way of writing an antiderivative. Here's another way of writing an antiderivative. Definitely prefer having a nice formula. Example 3. Suppose I do this. The integral from t equals 0 to t equals x of e to the minus t squared, and I park in front of that the derivative symbol. What is that? Cooper's hand's up. I want to get some more hands up. Is your hand kind of up? When you're doing this, if you were at Sotheby's, you would have just bought the painting. My son is trying to get the solo stove working. It'll wait. So, who knows what this is? Yeah, Jonah. Yeah, but don't pose it as a question. Sing it loud. Yeah, this is just another one of these things. You pluck out the integrand, which is e to the minus t squared, and you change the variable. That's our quest. Remember? We did not have a function that could serve as an antiderivative of e to the minus x squared. Every time we tried a function that we thought maybe could be an antiderivative of e to the minus x squared, we couldn't find one. So what we have just found is, let's make a picture of this. So this is the last thing we'll do today. But you're going to go off and tell your friends about this because this is really cool. You know, it's not what's called, it's a bell-shaped curve. It's not the bell curve. It's because it's not what's called normalized. The bell curve has some constants so that it's the same shape but a little bit slightly different details. And, you know, the question that we had before was, what's the function that when we take its derivative gets us this? And so far we've been striking out. Every time we tried a function up here, it didn't work. Turns out now we have one. So we could call this, say, capital F of x equals the integral from t equals 0 to t equals x. It's dangerous up here. I should be wearing a helmet, but I'm okay. So there we go. That's a way of writing a function that's an antiderivative of this. So it's not as cool as this, where we've got an honest function I can write down as an antiderivative. We've also got this wacky thing, this area function. And a while ago we had an antiderivative of t squared of x squared, of course, is x cubed over 3, or this wacky area function. But in this case, the only way that you can write an antiderivative of this is as an integral expression. And in your psychology books, in your chemistry books, in physics books, social science books, anytime you deal with the bell curve, which can be called the probability density function, you also deal with this kind of thing, which is called the probability distribution, which is just it's their jargon for an antiderivative of this. And furthermore, we have an expression for this. We don't have a formula for it, but we do know how it's going to have to look. Because look, when I take the derivative of a curve shaped like this, I get a curve shaped like this. It's going to have to be something like that going on over here. Even though I don't have a formula for this, I just have this integral expression. You can make a graph of this with a calculator or a computer, and its graph looks like this. And in your calculators, there's a button that will give you the y values on this graph as a function of x. Or you can look them up in tables of values in textbooks. So it's really amazing. We don't have a nicer formula. That's as good as it gets. All right, let's call it a day. See you tomorrow. Thanks everybody. If you didn't sign in now. Thanks, Gabriel.